megabytes.
144 gigabyte array.
Gigabyte. I have a 5.7 terabyte array.
Yeah, but yours are both spatters, platters.
Plus the screen is going to get recorded at the same time.
But we want
as you're pointing
speaker
at
and the screen.
I have
The screen.
It's just the cable.
Okay.
All right, very good.
Many thanks.
You're welcome.
Unless you do the
What I'm going to do is I'm going to start with this changing.
Okay. Many thanks for coming back and not forgetting that we have a class after a week of no class.
and we have a week of no class.
Huh? Well, you may have decided that it is a trend and we do not have class anymore. But we do. Yeah. So today we do have the presentations which complement our fourth chapter in the class. Before we had 3 chapters of time-independent perturbation theory, time-dependent perturbation theory, and angular momentum, is followed by applications or advanced chapters in form of presentation. And recently we went through non-equilibrium, non-linear time-dependent phenomena, starting from the background concepts. And today there is a chance of all class attendees to complement the boring and simple background material by summing blooming and more advanced chapters or applications. So what we do today includes 2 presentations on methods, 2 and 3, and then there will be 3 applications at the end, and there is 1 application at the beginning with the following logic. The presentation number 1 is the only model that in principle can be pursued without advanced methods. It is one of the exactly solvable models that has exact solution without processing time-dependent Hamiltonian and special equations, but it is a good example that helps us to look from different angle on the interacting systems. And then there will be 2 advanced methodology methods and 3 applications of NMR, and it was a lot of interest to quantum computing, so there will be 2 presentations covering from different angles. So all your slides are uploaded to this PC, and they are numbered and labeled according to your name. So 1st, 2nd, 3rd, 4th, 5th, 6th. So if you suddenly forget what to do, you just find number in your name, click, and it does pop up. If you dislike PowerPoint and your presentation is in PDF, you have option either run it in PowerPoint or in PDF. Here. Here. So we should try to finish within like hour plus something. So let's plan on staying no longer than 10 minutes up front. Everyone is invited to please speaker by questions. And with this, I would like to announce the presentation by Javed Abu Mohammed, who will tell us about atom in the cavity of magnetic field with James Cummings model. So try to stay in this area.
Oh, okay. Thank you. And so I'm going to talk on the James Cummings model about this one, and especially in the photon cavity, how the two level system interact with the photon. So if we look on this one this picture is one of the representation of the cavity system. If we apply the photon, it's going there, and because of when this absorbs some photons, and the number of photon is decreasing here, and again it's emitting, so it's getting, so it's making a cavity here. That's why it's known as a cavity system. And so first Janssen Cumming is first analyzed this such two-level system in 1963, and considered that two levels only: ground state and excited state. And then if we consider the other similar system like a Rabi interaction system, they consider that interaction dE by this one only, dE cos omega t. But in these cases, in the James Cummings model, they consider as a photon interaction, as a photon, not as a continuous wave function. So that's why they define the interaction cavity field E with this formula. In these cases, this one is annihilating and creation operator here to make a photon and create an absorbing photon. So now, if we want to make a Hamiltonian for this system, first interaction Hamiltonian is defined by this term, and where D is defined by D1, this is making a dipole, and E is giving you the direction of the dipole things. And atomic transition operator is giving us by this one can be comparable with the Pauli matrix, Pauli spin matrix. You can compare these two, and so that's why it's giving us these two cumulative. This relation we can get it from here, and the dipole operator D is defining by the two state, only ground state and excited state, and finally we'll get this one. And so so there are three different effects. One is the interactions with the photon and the two states, and this one is the atomic Hamiltonian, where the atomic energy is defining by this one is from these two as a Pauli matrix, and the free field Hamiltonian will define by this one is annihilation and creation operator of the photon. And then if we add these three terms, we will get this Hamiltonian from these three terms, and this Hamiltonian is known as the Janssen-Cumming Hamiltonian. So if we want to know the electron dynamics of this one, and if another one is if we solve these two terms, we will get this one, because sigma minus and alpha plus, we consider the 0, 1, and alpha plus is alpha, sigma plus and alpha is consider another two will be 0, and finally we'll get sigma plus alpha plus sigma minus alpha dagger. And then if we want to calculate the transitions, first we consider another operator. This is called actual number operator, I guess, and it will give us the number of photon in the system. And we want to divide this Hamiltonian, Janssen Hamiltonian, the two different Hamiltonian, H1b and H1b H2. These two Hamiltonian are defining by this one, H1 and H2, and both one, I mean H1 and H2, both are suddenly I forgot one very common term. They commute, this one, they both are commute with H1 in this research. And if we look, I skipped some mathematical formula. If this one is H1 cannot change the basis of the wave function, it only changes the number of, it also accumulates the phase only. It doesn't accumulate the phase. Accumulation of phase with the time is depends on this Hamiltonian. And so if we want to construct the basis, we will get this basis from the initial state and ground state. We consider this one excited state as the initial state, but this form also can be solvable as a considered ground state as a initial state. So this one is the initial state, and by emitting a photon is going to the ground state. Because of emitting is increasing the one number of photon here. That's why is n plus 1. If we consider the ground state as the initial state, it will go to excited state and photon number will be n-1, we will get the final state. And this is a linear combination of these two states. And if we put this in the time dependent Schrodinger equations, and then if we solve the equations from here, we will get this one, and then finally we will get two coefficients here, this one and this one, and from these two we get the probability of the electron populations in the ground state and excited states. So this one is the initial state, this one is the final. Initial means is excited state. In our case, the final state is the ground state. This will give you the population in the initial excited state and final state at time t. Now we want to look on the atomic inversions, the electron transition from ground to excited state to ground state. We can calculate from here by these equations, and this term is known as a Rabi frequency, this term, and then we can calculate here. And if we plot this one, we will get this symmetrical inversion of these electrons from ground to excited state. One interesting thing of Janus model and Rabi frequency model is when electron going to excited state, if you stop the radiations, that electron wouldn't go down there in the ground state. It will come in the excited state. But in the Janus model, if you stop the radiation, it will continue this process. It will emit the photons going to the ground state and absorb the photon again. It will go to the excited state again. So, and now we want to look on this solution in coherent state. So in coherent states, we can define this state by here in the ground state and excited state, and a field by this term. This is a coherent state, the different number of photons with this number. And now in the ground state, the basis we can define by this one is atomic basis and the field basis with the direct multiplication of these two one. And if we solve all of this by putting in the Gauss and the Schrodinger equations, we will get the in time ground state wave functions, and this one wave function. This depends on these two terms. And from all other maths what we did, and we can calculate the inversion of the atomic inversions of the incoherent state. And if we solve this one, we will get this coherent, inversion functions. And if we plot this one, we will get this type of plots. In its term, this, if we look on this first, it will show the two different states. This one is known as one is variable state, and there are two different names of this state and this state. I just forget this one. And if we continue this propagations for longer time, we will see that the this two state is going closer now here. That means it's almost like in the Rabi system in the longer time. So this is one of the main difference of this Janus model and Rabi system. So at the larger number of n, we will get this compact system, and if there is a small number of n, we will get this one. In this case, t is defined by lambda t here, and so we will get this one. So this is the Janus system model, and we can, I skip all other derivation, we can get a Jersey state. Jersey state means this state can be produce the two discrete states. It depends on the number of n, and we also derive some other factors too from the Janus model.
Okay, let's thank Jabit. And questions are welcome. If there are, yes, please.
You point to the diagram and you see this state and that state. I don't. This one and this one. Well, on both.
These are same one. Is plotting the WT with the time. So when the shorter time is showing this, I forget the exact name of this. Is it there's an invariation or this, because it's going to the 0 here, and then it started to fluctuate again. But with the longer time, this del t is going to smaller and smaller.
Diane, would you allow me to
I
ask
forgot
some
the
similar
exact
question?
word, so yeah.
So I had the same question in maybe a little different words. Right now, you are showing expectation value of the SZ spin projection, right?
Yeah.
For this two-level system. If you compute other two, how would this dynamic look on the Bloch sphere? Specifically, what will be the length of the Bloch vector, especially at the initial interval of time? Would it stay constant or it will change?
In this case, it will be constant.
Length. Brandon? Would you like to share your opinion and maybe try to help him?
I'm sorry, what was that? I missed the question.
Will you see any connection between this event that Jabet is showing and free induction decay? Would the length of Bloch vector stay constant or decrease?
Probably decrease.
Probably decrease. Okay. More questions to Jabet? So it is a prototypical analog of relaxation, right?
Yeah.
So it comes to 50% of population in ground and excited. On a short originally
yeah.
until here,
Yeah.
right? So it is importance and impact of this model. It shows mechanistically how one can shorten the length of the Bloch vector and how one can change the population.
So is the envelope of this function related to the length of the Bloch vector, or?
Well, you need to compute two other projections. Then it will look a little differently. But it will take
just for SZ.
Yes. Good. More questions? Can you go to slide number 2? Or yes. Here. So you are representing electric field by a summation of these two operators. What do you do? Why? How do you interpret it?
This one is actually, I mean, this one we consider as a photon, as a quantum energy. Is annihilation and creation of photons.
So you wanted to say
yeah.
that mode of electromagnetic field is a harmonic oscillator.
Yeah, kind of.
Okay, very good. Let's thank Jabet once again. So the next presentation will be by Aaron Cordia with a little more insight into methodology, and he will logically continue this idea. If here in the presentation by Jabet, we were looking on the dynamics of two levels, of this two-level system. But it was affected by interaction with one harmonic oscillator. And we saw that something that looks like relaxation happens. Aaron will try to share his vision and opinion what happens if there will be more than one oscillators, if they have other than photon nature, for example, phonons, and is there any use of so-called autocorrelation function in describing this phenomenon? Floor is yours.
So for my presentation, I'll be talking about how correlation functions are used to get dissipation rates in the density matrix. So essential concept here is, what is a correlation function? So very generally, correlation functions, they describe, it's a measure of like how two variables depend on one another in time. So the easiest, maybe the best explanation is this figure here. So we're multiplying two functions together and we're seeing how it changes in time. So like you can view one stationary and we're moving the other function past it. And then these are just different notations on how the correlation functions show up in different notations. And specifically we'll be using autocorrelation functions for operators.
You mean when f equals g?
F equals g.
When it is in your first definition?
Right.
There is the same function.
Right, so it's overlapping the same function through time. So that's why it's called an autocorrelation. So it's auto meaning self. So an example here, hopefully this image. So, oops, I meant deposit. So if we go up to, so initially we see that there's two wave packets and they're exactly overlap. So you'd see a very high peak here, meaning that the multiplying is positive and they're in phase. If we move it across, so we see when we get out of phase, or when we multiply them two together, we get negative peaks here. So they're kind of like negatively correlated. The wave packet moves further, you get another region where they're in phase again, so you get a little positive peak there. Then eventually they just kind of, the other one just drifts by the other one. If you plotted the correlation function for each time step, you'd get a plot that looks like this. So this is the initial state, and this would be when they're out of phase, comes back into phase, and then they just kind of pass towards each other. So that's a visual representation of what the correlation function represents. And then there's an important parameter which we call the correlation time, TC. So that's like the amount of time it takes for the two operators to be not correlated with each other anymore. They're basically independent, which is important because for operators we like them to be move. We want our operators to be independent of one another. So when we do our equations, that we can make them independent of one another, which simplifies the equations quite a bit. So the importance of these autocorrelation functions is that we can describe rates of transitions in terms of correlation functions. So if we consider Fermi's golden rule shown here, you do a little manipulation where you take the delta function and you expand it as an exponential integral, and then you times by a Boltzmann factor. You can rewrite it in terms of correlation function shown here. And it looks kind of weird, but if you look at it and you look at the units, like you can show that it's a rate because you get joules squared times seconds, and then there should be another factor of h bar out here, so you get divided by h bar squared. So you get joules squared seconds divided by joules squared seconds squared, so you get 1 over seconds. So that's why that's a rate. And then we can only use correlation functions under the Markov approximation. So we're not really integrating necessarily here, so we're considering time steps that are bigger than, like, we're talking about discrete time steps. So if we look back here, we're looking at, we want our time step to be bigger than this correlation function here, so that our operators will be independent of one another when we do the calculations. So that was it about correlation functions. So now we'll use them to get our dissipation rates for electron-phonon coupling and density matrix formalism. So the electron will be our system where we have it in some out of equilibrium state, relaxing, and it'll give energy to an ensemble of harmonic oscillators, which is represented by the lattice there. So first we start off with the Louisville equation and the second order perturbative correction. So this would be just our regular, this first term here would be just our regular Louisville equation, and the second term provides like our dissipation rates, or it's the second order perturbative correction. And then since we're only interested in the dynamics of the system, we can take the trace of the Louisville equation here, and we can basically integrate out all the variables associated with the phonon, or the bath degrees of freedom. So that's what these trace operations here are representing. And this is like a general solution. We haven't made any assumptions about our potential and our density matrix yet. So the first assumption for the density matrix is that the heat bath will always be in equilibrium and that our system will change in time. So we can break our density matrix into the density of the system and then of the heat bath, which is always going to be at equilibrium times 0. And you can think about it as like if you jump into the Atlantic Ocean, right? Like you're not going to change the temperature of the ocean at all. You're going to give some energy to it, but it's still going to be like negative 40 degrees or whatever. Or I mean 40 degrees Celsius, not negative 40 degrees. Or 40 degrees Fahrenheit, I don't know. But you get the idea. And then the second assumption that we make is that our operators are independent of one another, or that we consider time steps larger than the correlation between the two operators. So f of t will be our heat bath operator in the interaction picture, which is what all that stuff represents, and then the system operator, which is qt. So if we apply those two assumptions and then do a bunch of simplification, we can get to this result here. So the Louisville part disappeared, and then we're just left with the dissipative parts. And we can see that it's generally two parts. So we have commuters that are associated with the system of operators in density matrix. Then we have correlation functions over here associated with the bath and the bath operators and bath density matrix. So from here, we can make this equation look a little bit nicer by doing a couple of manipulations. So we can turn all these commuter terms here into numbers. If we take the time dependence, because in the interaction picture we have the two exponentials there. So if we take two electronic states and then convolute the operator, we can get a matrix product there and then pull the time dependence out. And then what we do with that time dependence, we put it in with into the integral with the correlation function. And then we do a change of variables and change our integration limits to make the computations a little bit nicer. So we change our variables so that here we have two. They both depend on a parameter of time, but we can shift them or shift our origin. So one of them is stationary, and then the other one, we're just integrating over that variable. So t double prime, or t prime to t double prime, and then t to 0. And then we take our integration limit, we just go to infinity, because after a certain amount of time, we're just adding a bunch of zeros. So it's not going to change the value of the integral at all. So with those two approximations there, we get scalars or matrix elements out in front, and then we have the autocorrelation functions which provide our rates. Here we get two rates because if we go back, we had a plus and a minus term here, so that's why we have a rate plus and a rate minus. And then skipping a couple of approximative steps here, we can use those rates, which they label as W, just summing the two rates together. But we can get changes in the occupation states of the density matrix. So time evolution of the matrix MM. MM represents a convolution between bra and ket M and M. So we get two terms here, which can be interpreted as states from M that go to M, and then states from M that go to other states. So it's basically the gain electrons coming to state M and then electrons leaving from state M, the state that you're considering. So then that's how we can use autocorrelation functions to get our rates for transitions between electronic states. So in summary, correlation functions are a pretty powerful tool that we can use to describe rates of transitions in our systems. And then the time evolution of the density matrix requires the Markov approximation so that we consider time steps larger than that the operators are correlated, so that we can get nice linear equations out of them. That should be it.
Okay, let's thank Aaron. Any questions?
You had an integral that early in the presentation that you went over the units that showed that it's a rate.
Yeah, so this one here, yeah.
Yeah.
So
H bar is 1 over energy seconds, right?
right, there should be another, because the reference that I use, they use gamma over H, so there's no H up here. So there should be an H there, then you get an H bar, or 1 over H bar, so you get H bar squared in the denominator here. So you get
how do you get it squared?
Because it's easier if I have to just write it out.
Oh.
So if you have, so the source I used, they said K is equal to gamma over H bar. So then they go gamma I divided by H bar divided by H bar. So that's where the extra factor of H bar comes from.
Satisfied?
Huh?
Satisfied? Okay,
That's okay. I will look it up.
more questions.
It looks to me like the integral is over time. So the whole integral
itself is in units of energy.
Right, so
you
you
get
get-
energy
so this is
over
the
energy seconds. So it's energy over energy seconds, which is 1/seconds, right? Which is great. I was just confused why I said it's energy seconds over energy squared seconds squared.
Do you oppose the final result? Or you oppose